In the beginning, there is only a sense of scale we think we understand. We look up at the sky, see a scattered arrangement of stars, and assume we have some grasp of the universe we live in. But the truth is far more disorienting than anything our senses can prepare us for. Imagine starting from the familiar, your room, your city, your country, and rising upward as though a silent camera is lifting off the ground. The world curves beneath you, oceans swirl like giant blue strokes of paint, and clouds drift lazily across continents. Earth already feels small, like a fragile ornament suspended in the dark. But this is only the first step. Climb higher and the moon pulls into frame, a pale companion circling us endlessly. From this vantage point, Earth is just a glowing sphere wrapped in a thin veil of atmosphere. The silence is absolute, the stillness almost unsettling. And yet, if someone were to place a dot on the screen showing your position, it would be too tiny to see. Your entire life, your memories, victories, regrets, the people you've loved and lost, all of it already compressed to something invisible. But the zoom-out continues. The Earth-Moon system becomes a pair of faint orbs. Soon they disappear entirely as the camera ascends into the solar system. The sun dominates the scene now, a furious, boiling sphere of plasma, its surface churning with loops of fire thousands of times taller than Earth. You could fit more than 1 million Earths inside it, yet even the sun is dwarfed by the space around it. Planets circle like silent, obedient sentinels, spaced so far apart that each one feels like a lonely island surrounded by a black ocean. You keep rising. The outer planets shrink into tiny specks. Neptune vanishes into darkness. The Kuiper belt fades. And then the solar system itself collapses into a single sparkling dot, a grain of dust suspended in a boundless void. But the zoom-out doesn't stop. That lone dot, the one containing our sun and every planet we have ever known, drifts into a cloud of billions of other stars. The Milky Way begins to reveal itself. First as scattered points, then as clusters, then as a glowing mist wrapping around a spiral arm. The camera continues pulling back until the entire galaxy comes into view, a colossal whirlpool of stars, dust, gas, and dark matter stretching 100,000 light-years across. In this majestic swirl, our solar system is unremarkable, not marked by any special glow or pattern. It is lost in an ocean of starlight so vast that even if you knew exactly where to look, you still wouldn't be able to find it. It is like trying to locate a single grain of sand on an entire coastline. And even that comparison feels generous. Now the camera holds still for a moment, as if inviting you to absorb the overwhelming disparity. This is the scale we live in. This is the home we never truly see. The Milky Way rotates slowly, arms stretching outward like the silent currents of a cosmic hurricane. Every point of light is a sun. Many of those suns host planets. Some of those planets may host life. And on one of them, in a quiet corner of a quiet arm, human beings built cities, created stories, fought wars, fell in love, and wondered what their place in all of this might be. A strange tension builds here, between awe and insignificance. The galaxy is beautiful, almost impossibly so, yet its size makes our entire history feel like a whisper in a storm. If everything we are can disappear into a single pixel from far enough away, what does that say about the meaning we attach to life? Do our achievements matter when the universe is so unimaginably large? Or is there something profound in the very fact that consciousness emerged at all in such a vast, indifferent place? The zoom-out resumes again briefly to emphasize the emptiness. Surrounding the Milky Way is darkness, not a simple absence of light but a deep cosmic void filled with invisible structures, wandering stars, and ancient radiation. Even the galaxy, enormous as it is, becomes just another glowing smudge among countless others. It is no longer the center of the story but one character in an infinite ensemble. And still, we return mentally to that vanishing point hidden somewhere inside the spiral arms. That invisible location where you exist, where your heartbeat echoes inside a body made of stardust. The contrast is staggering. One life set against a canvas billions of light-years wide. Yet this contrast is the heart of the mystery. How can something so tiny produce ideas, emotions, dreams? How can something almost too small to register on a cosmic map dare to contemplate the universe itself? As the camera holds the galaxy in full view, suspended like a brilliant island in a black sea, a final unsettling thought rises. If this is our scale, if this is how small we truly are, then what else lies out there that we cannot even begin to imagine? The Milky Way is often imagined as a gentle, serene swirl of stars, an elegant pinwheel drifting peacefully through the cosmos. But beneath that graceful appearance lies a story carved by giants, forces so massive and ancient that they defy the limits of human imagination. To understand how tiny we truly are, we must first understand the immense architecture of the galaxy itself, built not by delicate starlight, but by titanic structures that silently dictate everything within them. Picture the galaxy in its earliest moments. A chaotic sea of collapsing gas clouds, cosmic storms roaring across light years, and primordial matter gathering into the first colossal formations. These were not gentle processes. They were violent, catastrophic, and relentless. The universe sculpting itself through explosions and gravitational collisions. What we now call the Milky Way was born from this cosmic turbulence, shaped by entities so enormous that even calling them giants feels inadequate. Consider, for example, the molecular clouds. These vast regions are the birthplaces of stars, but they are not clouds in any earthly sense. They span hundreds of light years, dense enough to form thousands of suns yet fragile enough that a shockwave from a distant supernova can tear them apart like paper. Within these clouds, threads of gas begin to coil and twist, pulled inward by gravity until they spark into new stars. These clouds are the wombs of the galaxy, but their scale is so staggering that the Earth could be dropped inside one and remain unnoticed forever. As these clouds collapse, they give rise to star clusters, tight congregations of newborn suns glowing like embers in a cosmic forge. Some of these clusters are enormous clusters packed with millions of stars, each radiating intense heat and brightness. Others are smaller but no less beautiful, drifting through the galaxy like shimmering islands. Humanity has catalogued only a small fraction of these clusters, and yet they form just a thin sprinkling across the galactic landscape. Now shift your gaze to the spiral arms themselves, the vast, sweeping arcs that define the iconic shape of the Milky Way. Each arm is not a solid structure, but a flexible, shifting wave pattern made of stars, dust, and gas. These arms are so thick that it would take light hundreds of years to travel from one edge to the other. And yet from afar they appear delicate, almost artistic in their design. This is the contrast at the heart of galactic formation, beauty made from chaos, order emerging from unimaginable scale. These spiraling lanes act as star factories, compressing matter over millions of years and igniting new suns. Without them, the galaxy would be a dim, irregular cloud instead of the luminous will we see today. Even more astounding are the supergiant stars scattered throughout the galaxy, massive suns that dwarf our own star into insignificance. Some are dozens, even hundreds of times more massive than the Sun, burning with such intensity that they live fast and die explosively. Their deaths reshape the galaxy, sending shockwaves that stir molecular clouds and trigger new rounds of star formation. These stars are the architects and the destroyers, influencing regions thousands of times larger than their own size. Humanity has never seen most of these behemoths directly. They lie hidden behind curtains of dust or too far from Earth for our telescopes to resolve. Yet their presence shapes the architecture of the Milky Way like silent celestial monarchs. Then there are the giant gas clouds, huge drifting structures made of hydrogen, helium, and mysterious trace elements. Some of these clouds span thousands of light years. They are the rivers of the galaxy, flowing slowly and invisibly, carrying the raw materials for star formation. Their edges are shaped by ancient collisions, supernova remnants, and gravitational tides. If you could float inside one, you would see nothing but a dim haze. The human eye is too weak to perceive its true scale. But viewed from afar, these clouds are pillars of creation, the scaffolding on which the galaxy builds its stars. Dark matter is yet another giant, an unseen titan whose presence outweighs everything visible in the Milky Way. We cannot see it, touch it, or measure it directly. And yet it forms the hidden skeleton of the galaxy, a colossal framework that holds everything in place. Without dark matter, the Milky Way would fly apart. Its stars would drift into the void. This invisible giant exerts a gravitational pull so vast that it shapes the orbits of stars we will never see and governs the motion of the galaxy as a whole. It is a ghostly architect, omnipresent yet unknowable. Scientists estimate that nearly 90% of the galaxy's mass is dark matter, meaning the Milky Way is built almost entirely from something we do not understand. All these giants, molecular clouds, star clusters, spiral arms, supergiant stars, and dark matter, work together to build the galaxy we inhabit. Their existence adds weight to the humbling truth that humanity lives in a structure far older, larger, and more powerful than anything we could create. Even the familiar stars we see in the night sky are mere flecks compared to the enormous forces shaping the galaxy. And yet, despite the scale of these colossal structures, we live unaware of their presence. Our view of the Milky Way from Earth is filtered through a thin slice of the sky, obscured by dust, light pollution, and the limits of human perception. What appears to be a narrow band of starlight is actually a cross-section of an immense, three-dimensional structure that stretches across more than 100,000 light-years. We navigate our lives without ever seeing the giants that sustain our galaxy. Still, the greatest mystery remains: how did all these structures come to exist in such harmony? Why did the galaxy settle into its spiral shape? How did dark matter gather around it like an invisible shell? Why do clusters form in some regions but not others? These unanswered questions linger like distant echoes from the galaxy's past. As we consider the magnitude of these giants, a subtle emotional tension forms. There is awe in knowing that we are part of something so magnificent, yet fear in realizing how small and fragile we are in comparison. Humanity occupies a tiny space within a gigantic machine of stars and forces, a whisper inside a storm of creation. And the deeper we look into the structure of the Milky Way, the more we realize how little we understand about the giants that built it. If these enormous forces could shape an entire galaxy, what else might they be capable of, beyond our detection, beyond our comprehension, beyond anything we have imagined? The Milky Way is not just a galaxy. It is an ancient, sprawling metropolis built across the silent canvas of space. If we could drift beyond the dust and darkness that hide its true form, we would see a glowing city of stars stretching across 100,000 light-years. Each spiral arm would appear like a luminous district, some crowded, some abandoned, some pulsing with newborn stars, others haunted by the remnants of long-dead suns. And in this vast cosmic city, humanity occupies a single, unremarkable neighborhood tucked away in a quiet corner. Yet the deeper we explore this galaxy, the more we uncover hidden realms, secret structures, and mysteries older than life itself. Imagine standing at the edge of the galaxy, looking inward. The spiral arms curve around the bright core like avenues leading toward a radiant downtown. These arms are alive with activity, star formation regions blazing in pink and blue, molecular clouds drifting like fog between skyscraper-like clusters, supernova remnants glowing like shattered neon signs marking ancient explosions. The arms are busy districts, crowded and full of chaotic beauty, where stars are born, live, and die in an endless cycle. If you traveled along one of these arms, you would witness phenomena so intense and colossal that they would challenge every notion of scale you've ever had. Closer to the center of the galaxy lies a region unlike anything we can truly imagine. Here, gravitational forces pile stars together so densely that they appear as a continuous sheet of light. The core glows like a blinding city center, a place of scorching radiation and restless motion. Stars whip around the central black hole at thousands of kilometers per second. Gas clouds collide, stretch, and break apart. Everything here burns brighter, moves faster, and lives shorter. It is a district of relentless pressure, brilliant beauty, and terrifying power, an urban furnace in the heart of the Milky Way. But as we move outward from the center, the galaxy begins to change. The busy brightness fades into suburbs where stars are spread farther apart. Here, clusters drift more calmly, stellar nurseries glow softly, and the chaos of the core gives way to something more familiar. Quiet neighborhoods of long-lived stars, stable planetary systems, and gentle cosmic weather. This is a region where life has a chance to exist, if it ever forms at all. These calmer suburbs stretch across much of the spiral arms, offering islands of stability within the swirling storm of galactic evolution. Yet even in these quieter regions, hidden structures shape the galaxy's appearance. Interstellar dust forms shadowy lanes that weave through the arms like dark streets cutting between glowing blocks of stars. These dust lanes are dense enough to hide entire clusters, obscuring vast stretches of the galaxy from view. There are star-forming factories buried inside these lanes, places where gravity compresses gas into fiery newborn suns. From Earth, these areas look like voids, empty and dark. But in reality they are bustling with activity. The cosmic city is always building, always changing, always in motion. Beyond the spiral arms lies another kind of neighborhood entirely, a halo of ancient stars and ghostly globular clusters. These clusters are some of the oldest residents of the galaxy, relics from a time before the spiral structure even formed. They drift above and around the main disk like forgotten outposts, their stars tightly bound together in dense spheres. Each cluster may contain hundreds of thousands of stars, many of them older than Earth, older than the Sun, older than the galaxy we know today. These are the archives of the Milky Way, silent guardians of the past that orbit in the darkness far beyond the bustling districts below. But the Milky Way is not a city made only of stars. Scattered throughout are rogue planets, worlds without suns, wandering like drifters through the galactic streets. There are ancient stellar corpses, white dwarfs cooling slowly in the dark. There are neutron stars spinning with deadly precision, emitting beams of radiation like cosmic lighthouses. There are regions of hot plasma, remnants of supernova explosions that stir the interstellar medium. There are magnetic fields that twist and ripple invisibly, shaping the behavior of particles and gas across light years. Every component contributes to the larger city, each part interacting with the next in a complex, evolving tapestry. Yet even with all this structure, much of the galaxy remains hidden from our eyes. Dust blocks visible light. Distances distort our perception. Time itself becomes a barrier, as light from distant regions takes tens of thousands of years to reach us. When we map the Milky Way, we are not seeing it as it is, we are seeing fragments, shadows, and echoes of what it was long before humans walked the Earth. Parts of the cosmic city lie forever out of reach, concealed behind impenetrable clouds or too far away for our instruments to resolve. It is a place of both breathtaking clarity and unsettling darkness. Despite the galaxy's vastness, humanity exists in only the smallest of its many districts. Our solar system lies in a faint, quiet branch of the Orion Arm, far from the galaxy's luminous center. It is a modest neighborhood, peaceful compared to the core, dim compared to the massive arms, and unremarkable in almost every way. Yet here, on a tiny planet orbiting an unexceptional star, life emerged. Consciousness awakened. A species arose capable of questioning its place in this cosmic city. This contrast, the insignificance of our location versus the enormity of our curiosity, creates a tension that runs through our entire understanding of the universe. We wander through the galaxy not with spacecraft, but with telescopes, mathematics, and imagination. We map the regions we can see, infer the structures we cannot, and build models to fill in the gaps. Still, our knowledge is incomplete. There are districts of the Milky Way we have never observed directly. There are star-forming regions so heavily shrouded in dust that no visible light escapes from them. There are star clusters hidden behind brighter regions, camouflaged by the glow of the spiral arms. There are voids and pockets where hardly any stars exist at all. Every year we discover new structures, filaments, bubbles, ridges, streams, most of which were invisible to us just decades ago. This cosmic city, as vast and ancient as it is, remains full of unanswered questions. Why do some regions burst with star formation while others remain silent for billions of years? How many civilizations might be hidden within its countless neighborhoods? What colossal events shaped its past? Collisions, mergers, gravitational upheavals? And what forces are shaping its future even now? And most haunting of all, what lies in the hidden districts we can never reach, never see, never understand? The Milky Way is a city of wonders and enigmas, built on scales that overwhelm the human imagination. It is ancient beyond measure, ever-changing, ever-expanding, filled with beauty and danger in equal measure. And as we drift through one of its quiet neighborhoods, separated from its luminous heart by thousands of light years, we are left with a single lingering question. What secrets lie in the parts of the cosmic city where no light reaches us at all? Our solar system is a tiny district within the sprawling metropolis of the Milky Way, a modest neighborhood tucked into the Orion Arm, far from the galaxy's luminous center. If the galaxy is a vast city, then the Sun and its orbiting planets are a quiet cul-de-sac, almost invisible against the brilliance of the cosmic skyline. From this perspective, Earth is not a planet. It is a pale, fragile ornament, barely noticeable, drifting along the outskirts of a region filled with billions of stars. Yet within this small enclave lies everything we know, our history, our civilizations, our dreams, our lives, all contained within a fragile bubble of gravity and light. Imagine leaving Earth and moving outward through the solar system. The moon, once so familiar in the night sky, becomes a barren, lifeless rock in the void, orbiting a glowing blue and green jewel. The planets stretch out along invisible tracks, each separated by vast distances that challenge human intuition. Mercury, the closest to the Sun, races along its orbit in a scorching, cratered landscape. Venus glows with thick clouds of acid and heat, its surface hidden behind a veil of toxic yellow. Mars appears as a pale rust-colored dot, its deserts and canyons dwarfed by the emptiness surrounding it. Even Jupiter, a massive gas giant, dominates its region with swirling storms the size of continents, yet it is still only a minor feature on the scale of the solar system itself. The distances between these planets are staggering. If you shrank the Sun to the size of a large beach ball, Earth would be a tiny bead orbiting at several meters away. Jupiter would be 15 times farther, and Neptune more than 30 times that. Vast stretches of darkness separate these worlds, regions where nothing exists except the occasional asteroid, comet, or invisible particle of dust. The solar system is not crowded. It is a lonely, isolated neighborhood, a fragile island of order in a vast cosmic ocean. Beyond the planets lies the Kuiper Belt, a distant, icy frontier populated by frozen worlds, dwarf planets and ancient remnants of the early solar system. These objects drift silently in the outer reaches, untouched by sunlight for decades, centuries, or even millennia. Some of them are as small as mountains, others rival planets in size. They are relics of creation, holding secrets of the solar system's formation, yet they remain largely unexplored, their silent paths weaving through darkness that humans have only begun to probe. Beyond even that lies the Oort cloud, a hypothesized shell of icy bodies extending nearly halfway to the nearest stars, a boundary so distant and diffuse that it defines the outer edge of the sun's influence. Despite the emptiness, this tiny district is not static. Gravitational tugs ripple outward, resonances between planets and asteroids create subtle dances, and the sun itself travels through the galaxy at incredible speed, carrying its planetary family along a vast orbit around the Milky Way's center. Everything in the solar system is moving, and yet from our tiny perspective on Earth, it all seems still, calm, and eternal. This contrast is crucial. The apparent serenity of our neighborhood belies the immense forces and motions at work, forces that dwarf our senses and make our familiar world feel almost unreal when placed in context. Even within this small space, there is a profound fragility. The asteroid belt contains remnants of a failed planet, vast chunks of rock and metal capable of mass destruction. The inner planets are subject to impacts that could erase civilizations in an instant. Solar flares and coronal mass ejections from the sun can disrupt the delicate balance that sustains life. The solar system, though seemingly stable, is a delicate construction maintained by precise conditions and improbable alignments. Its serenity is not guaranteed. It is a temporary calm within a dynamic and sometimes violent universe. And yet, within this fragile bubble, life has flourished. On Earth, oceans teem with life, forests stretch for thousands of kilometers, and human civilization has emerged, capable of understanding its place in the cosmos. From this tiny, insignificant corner of the galaxy, we have glimpsed distant stars, measured cosmic distances, and even sent instruments beyond our own planetary neighborhood. The very fact that life exists here, in this small, unremarkable suburb of the Milky Way, is astonishing. It reminds us that even the most modest district in a colossal city can hold marvels beyond comprehension. The solar system is a neighborhood of contrast. It is immense and empty, yet full of planets, moons, and debris. It is stable and predictable, yet subject to chaos and destruction. It is our home, intimate and familiar, yet when seen against the backdrop of the Milky Way, it is almost invisible. Every world, every orbit, every small rock is part of a larger story, a story of gravity, motion, and cosmic evolution that has unfolded for billions of years. Understanding the solar system in this context reshapes our perspective. What feels vast and limitless when standing on Earth is tiny when viewed from a galactic scale. We are not at the center. We are peripheral observers in a quiet, modest neighborhood, drifting through a city of unimaginable size. This realization can be humbling, even unsettling, yet it is also a source of wonder. For in this small district, life emerged, consciousness awakened, and beings capable of questioning their place in the galaxy began to exist. As we move further outward, leaving the known planets behind, the solar system collapses into a tiny point, a speck in the immense, swirling Milky Way. And it is here, in this barely visible dot, that all human history, achievement, and imagination are contained. The contrast is staggering. Our vibrant, complex lives occupy a space that, from a cosmic perspective, is nearly imperceptible. Yet it is within this dot that the story of humanity begins, a story that will continue to unfold, even as the galaxy turns slowly around its invisible center, carrying our tiny neighborhood along its spiral arms. In this way, the solar system is more than just a collection of planets. It is a delicate, luminous island within a sea of stars, a fragile bubble of stability in an otherwise indifferent cosmos, and the starting point for understanding just how small we truly are in the grand scale of the Milky Way. The Sun, our seemingly familiar star, occupies a peculiar and lonely position within the Milky Way. Unlike the dense, radiant core of the galaxy, where stars crowd together in an almost blinding assembly, the Sun resides in a sparsely populated suburban arm, a quiet outpost drifting through a cosmic countryside. It is neither central nor exceptional, merely one star among hundreds of billions. Yet for us, this ordinary star is the source of all life, light, and warmth. Its location, far from the galactic core and nestled between neighboring stars, is a delicate balance that has shaped the evolution of our solar system and ultimately our very existence. Imagine the Milky Way as a city at night. The core glows like a brilliant downtown, bursting with neon signs and flashing lights, the domain of stars burning with unimaginable intensity. Surrounding this central hub, the spiral arms fan outward, gradually fading into dimmer suburbs and then into the quiet, almost empty outskirts. The sun drifts in one of these suburbs, a pale, solitary street lamp in a vast, dark neighborhood. Here, stellar neighbors are scattered widely. The nearest star, Proxima Centauri, lies over 4 light-years away, a distance that highlights the isolation of our sun. The neighborhood is peaceful, almost eerily quiet, a sharp contrast to the dense chaos of the galactic center. This position is not random. Astronomers believe that the sun's location in the Orion Arm may have contributed to the stability necessary for life to emerge on Earth. Being far from the galactic center spared our planet from the gravitational turbulence, intense radiation, and frequent supernova explosions that dominate more crowded regions. If we were closer to the core, our solar system could have been shredded or sterilized multiple times over by the violent activity surrounding the densely packed stars. The sun's suburban placement provided a calm cosmic environment, a rare pocket of safety amid the galaxy's vast and often hostile expanse. Despite its apparent solitude, the sun is part of a subtle network. It moves along its orbit around the galactic center at an average speed of about 828,000 kilometers per hour, completing a circuit roughly every 225 to 250 million years, a period known as a galactic year. This journey is not smooth. It weaves above and below the plane of the galaxy, bobbing through the galactic disk like a boat navigating gentle waves. Along the way, the sun passes through regions of varying stellar density, cosmic dust, and interstellar gas clouds, sometimes brushing against these neighborhoods with barely perceptible effects on the solar system. It is a solitary traveler, yet not entirely isolated, carried along by the gravitational currents that shape the entire Milky Way. The sun's apparent stability is deceptive. While it shines steadily, its interior seethes with violent nuclear fusion, churning plasma, and magnetic storms that occasionally erupt as solar flares or coronal mass ejections. These eruptions ripple across space, affecting planetary atmospheres and sending charged particles streaming toward Earth. Even in its quiet suburban position, the sun is a dynamic, sometimes volatile presence, reminding us that isolation does not equate to calmness. The same star that nurtures life also possesses the power to disrupt it, a tension that defines our existence in its orbit. From a cosmic perspective, the sun is unremarkable. It is a middle-aged, medium-sized G-type star, neither extraordinarily massive nor particularly bright compared to the galaxy's giants. Supergiant stars blaze hundreds of times brighter and millions of times more massive. Black holes and neutron stars lurk unseen, exerting invisible gravitational forces across thousands of light-years. Yet despite its ordinariness, the sun's location, far enough from danger yet close enough to resources, enabled the emergence of planets, water, and eventually life. Its quiet placement in the galaxy illustrates how even small positional differences can have enormous consequences over cosmic timescales. As we trace the sun's orbit through the Milky Way, we begin to perceive the profound loneliness of its position. Unlike the densely packed downtown regions where stars jostle against one another in a crowded stellar metropolis, the sun's suburban neighborhood is spread out, quiet, and sparsely populated. This creates a strange emotional contrast. A star that sustains life is at the same time almost invisible on a galactic scale, a solitary beacon in a vast sea of darkness. It is neither the brightest nor the most massive, yet its position allows life on Earth to exist, flourish, and eventually become conscious enough to contemplate its own insignificance. This suburban placement also emphasizes the relative fragility of our existence. The quiet calm of the Orion Arm is not permanent. The Milky Way is a dynamic galaxy, constantly evolving, with stars moving, clouds colliding, and supernovae exploding in the distance. Over millions of years, the sun will continue its journey, passing through regions both safer and more hazardous, encountering interstellar clouds and gravitational perturbations. This motion highlights that even a safe position is temporary, a transient haven in a galaxy in perpetual flux. Ultimately, the sun's lonesome position deepens the sense of human insignificance when we consider the galaxy as a whole. From the central core to the farthest halo, stars cluster, burn, die, and shape the galaxy on scales that dwarf our imagination. In contrast, the sun drifts quietly through a sparsely populated arm, a modest star sustaining life in a small corner of one spiral arm, a lonely participant in a cosmic ballet of unimaginable scale. It is a reminder of both the fragility and the extraordinary fortune of our existence, a fragile light in a vast, largely indifferent universe. And yet, in this quiet neighborhood, the sun enables everything we know: the rhythm of days and seasons, the energy that drives oceans and winds, the light that reaches our eyes and nourishes life. Its loneliness is inseparable from its importance. This juxtaposition, insignificance in the grand cosmic scale, yet monumental influence within its local district, is central to understanding our place in the galaxy. The sun's position, its path, and its stability allow life to exist, yet also underscore the profound vulnerability of our small, solitary home in the quiet outskirts of the Milky Way. Our solar system does not float through the galaxy in isolation. It drifts along a vast, invisible river of stars, gas, and dark matter, carried by the immense rotation of the Milky Way. Imagine the galaxy as a colossal, spiraling whirlpool of light, each arm twisting gracefully through space like a river of fire and ice. Within one of these arms, the Orion arm, our sun traces its orbit, moving at incredible speed yet seemingly still to our senses on Earth. As we follow this path, we begin to perceive the Milky Way not as a static disk of stars, but as a dynamic, flowing system, a spiral in motion, alive with the slow, inexorable rhythm of gravity. Visualize drifting along this cosmic river. Stars ahead glow like distant street lamps, their light taking tens, hundreds, or thousands of years to reach you. Nebulae flare like clouds of colored smoke, rippling with energy from newborn stars. Dust lanes drift like currents, blocking and bending light as if guiding the flow of celestial traffic. Every star, every cluster, every planet follows a path dictated by the unseen hand of gravity. And through it all, our sun and its family of planets move as though caught in an imperceptible tide, sailing along the spiral arm on a journey that began billions of years ago and will continue for billions more. The motion of the galaxy is slow on human timescales, but immense in magnitude. The spiral arms themselves are not solid structures. They are patterns of higher density, waves of stars and gas moving together through the galactic disk. Like a conveyor belt, these density waves compress gas, triggering bursts of star formation as they sweep along. Stars orbit in near-circular paths, but their speeds vary depending on their distance from the center. The Sun, roughly 26,000 light-years from the galactic core, completes a full orbit in about 225 to 250 million years. Its orbit is a gentle, spiraling dance, bobbing above and below the galactic plane like a boat riding soft waves on a river of light. Within this motion, the scale becomes almost incomprehensible. The nearest stars to the Sun, Proxima Centauri and Alpha Centauri, drift tens of trillions of kilometers away, yet they too are caught in the same massive spiral flow. Entire clusters of stars follow their own orbits, some colliding, merging, or breaking apart over millions of years. Gas clouds, invisible to the naked eye, drift along these currents, compressed into brilliant regions of star formation or stretched thin across vast, empty spaces. Even the supermassive black hole at the galaxy's center exerts its invisible influence, tugging on stars across tens of thousands of light-years, subtly shaping the flow of the spiral arms. The interplay of motion, gravity, and mass creates a sense of organized chaos. The Milky Way is neither a rigid wheel nor a static pinwheel. It is a dynamic, living system, constantly evolving and reshaping itself. Stars move in predictable orbits, yet their interactions create ripples that propagate through space, shifting gas clouds, altering trajectories, and sometimes triggering explosive events. Cosmic collisions, though rare on human timescales, occur frequently in the grand history of the galaxy, shaping its arms, compressing material, and seeding regions with the elements necessary for planets and life. As our perspective follows the Sun along its path, a sense of motion emerges that is both majestic and disorienting. Though the galaxy rotates slowly compared to the speed of light, its vastness makes even gradual movement monumental. We imagine drifting alongside, carried forward at over 828,000 kilometers per hour, watching nearby stars glide past over millennia, nebulae expanding and fading, and clusters shifting imperceptibly through the darkness. Every motion tells a story: the birth of stars, the death of massive suns, the subtle tug of gravity between neighbors, and the invisible currents of dark matter that hold the galaxy together. This spiral journey emphasizes our insignificance yet also our connection to the greater cosmic dance. Every atom in our bodies, every planet in our solar system, every grain of dust in the asteroid belt is moving in concert with the Milky Way's rotation. Though we perceive the sky as still, we are all part of a vast, choreographed flow stretching across light years. The awareness of this motion brings awe, but also a subtle tension. In such immense, unceasing movement, our lives, civilizations, and even our entire solar system are fleeting, transient markers on an unending journey. There is a strange beauty in the contrast. From our human perspective, the stars seem fixed, eternal and unchanging, guiding sailors and inspiring dreamers for millennia. Yet, zooming out, we realize that nothing is stationary. Every point of light participates in an enormous spiral dance, moving through the galaxy at incomprehensible speeds, shaping and reshaping the structure over time. This revelation forces a reconsideration of scale. What seems permanent is fleeting, what seems immense is minuscule, and what seems isolated is part of a colossal interconnected flow. The cosmic river is not without danger. Streams of gas and clouds of dust can trigger catastrophic star formation or supernovae. Passing near massive objects can perturb orbits, sending comets and asteroids into new paths. Even the tranquil suburbs of the Milky Way, where the sun resides, are subject to these subtle, invisible currents. Every journey through the galaxy carries risk, yet life and the solar system have persisted through billions of years of motion, orbiting a galactic center that is both distant and indifferent to the tiny travelers within its spiral arms. Ultimately, drifting along the Milky Way's spiral arms illuminates a profound truth. Our existence is part of a larger, ordered, yet unpredictable flow. We are carried along in a vast current, moving through a galaxy teeming with energy, activity, and invisible forces. The cosmic river underscores both our fragility and our connection to the universe, showing that even a small solar system, quietly orbiting a modest star, participates in the immense, awe-inspiring motion of a galaxy alive with the slow rhythm of stars, gas, and gravity. Surrounding our solar system is a region of eerie emptiness known as the local bubble, a vast cavity carved out of the Milky Way by ancient cataclysms. This bubble stretches for hundreds of light-years in every direction, a hollowed-out neighborhood within the galaxy where the density of stars and gas is far lower than in typical regions. If the Milky Way is a bustling city, the local bubble is a quiet, abandoned district. Streets empty, buildings crumbled, and silence reigning over a space that was once roiling with energy. Within this void, the solar system drifts largely unperturbed, cushioned from the chaos that surrounds other, more crowded regions of the galaxy. Yet the emptiness itself tells a story, one of violence, transformation, and cosmic survival. The local bubble was formed by a series of supernova explosions that occurred millions of years ago, long before humans walked the Earth. These stellar detonations were not subtle events. They were catastrophic, sending shockwaves racing across space, blasting gas and dust outward, and clearing vast swaths of interstellar material. In effect, the stars that once occupied this region were violently removed, leaving behind a cavity of low-density plasma and tenuous gas. The bubble is a scar on the Milky Way, a monument to cosmic violence written in the language of emptiness. From Earth, we are mostly unaware of this history, but its presence shapes our environment in profound ways, influencing cosmic radiation, interstellar gas flows, and even the trajectory of nearby stars. Imagine floating through this space. Unlike the dense spiral arms or the crowded core, the local bubble offers vast stretches of almost nothing. The stars here are few and far between, scattered like distant lanterns in a desert. The interstellar medium is tenuous, filled with hot, ionized gas, invisible to the naked eye but detectable through specialized instruments. It is a space that feels both protective and isolating. Protective because it shields the solar system from some of the more intense interstellar disturbances that occur elsewhere. Isolating because it emphasizes the profound emptiness surrounding us, a vast darkness in which our sun is just a lonely point of light. Within this bubble, remnants of ancient supernovae still linger, drifting as hot clouds of ionized gas and cosmic debris. These remnants are ghostly traces of cataclysmic events, stretching for tens or hundreds of light years. Though the original explosions occurred long ago, their effects continue to shape the local bubble, pushing material outward, influencing the density and temperature of the interstellar medium, and subtly directing the flow of nearby stars and gas. It is a region that is both quiet and active, seemingly empty but alive with the echoes of violence past. The local bubble also creates a striking contrast with the surrounding galaxy. Beyond its boundaries, the Milky Way is dense with stars, gas clouds, nebulae, and star-forming regions. These outer neighborhoods teem with activity, full of the tumult and brilliance of cosmic life. In contrast, the bubble is a peaceful void, an almost eerie calm, where the solar system can orbit without frequent catastrophic encounters. Yet this calm is not eternal. The Milky Way is dynamic, and over millions of years, stars, gas clouds and other structures will slowly drift into or near this bubble, reintroducing turbulence and change. The local bubble is temporary, a transient sanctuary in a galaxy that never stops moving. Our solar system's residence within this empty region may have had significant consequences for the development of life on Earth. Shielded from the densest and most dangerous regions of the galaxy, Earth avoided frequent exposure to intense supernova radiation that could sterilize the planet. At the same time, the bubble is not completely empty. Cosmic rays, interstellar dust, and diffuse gas still flow through it, subtle reminders that the void is not benign. Life evolved in this quiet, protected neighborhood, taking advantage of a balance struck between exposure to energy and relative isolation. The local bubble is also a reminder of the impermanence of cosmic structures. What seems empty and stable today was once violent and chaotic. Over hundreds of millions of years, stars will move, new supernovae will occur, and the bubble itself may collapse or merge with neighboring cavities. The universe is in constant flux, and even the emptiest regions are subject to change. Yet for now, this hollowed-out space serves as a silent testament to the scale and power of the processes that shape the galaxy, a reminder that even emptiness carries the weight of history. As we contemplate the local bubble, an emotional tension arises. There is awe in recognizing the extraordinary forces required to carve out such a region, a reminder of the galaxy's violent past. There is fear in realizing that such violence could recur at any time, potentially affecting the delicate balance that allows life to exist. And there is wonder in understanding that within this sparse, seemingly empty neighborhood, our solar system drifts through space, largely undisturbed, a fragile oasis in a landscape forged by fire, death, and gravity. Ultimately, the local bubble reveals both the beauty and the fragility of our cosmic environment. It is a space where emptiness is more than a lack of matter, it is a record of creation and destruction, a subtle force that has shaped the evolution of our solar system, and a lens through which we can begin to appreciate the extraordinary scale, motion, and history of the Milky Way. Within this hollowed expanse, the tiny district we call home is preserved, yet constantly reminded of the immense power and violence that surround it, a quiet corner in an otherwise vast and unpredictable galaxy. Beneath the glowing stars and swirling gas of the Milky Way lies an invisible architecture that governs the galaxy's very existence: dark matter. Unlike stars, planets, or nebulae, dark matter does not emit light, reflect it, or interact with it in any way that we can detect with ordinary senses. Yet its presence is undeniable. It is the unseen skeleton upon which the galaxy is built, a ghostly framework that shapes the orbits of stars, dictates the flow of spiral arms, and holds the Milky Way together against the centrifugal force of its own rotation. Without it, the galaxy would unravel and our solar system, along with billions of others, would drift into the void. Imagine the Milky Way stripped of its dark matter. The stars would not form the tight spirals we see in telescope images, the galaxy would lose its coherence, and the magnificent whirlpool of light would scatter into isolated fragments. It is an invisible force, yet its influence is pervasive. From our vantage point on Earth, we experience only a tiny fraction of its effects, but on cosmic scales, dark matter dominates, outweighing visible matter by nearly 5 times. The stars, planets, and gas clouds that we can see are essentially passengers in a vast, unseen gravitational web, their paths guided by a force we cannot touch or see. Dark matter is thought to form a massive halo surrounding the galactic disk, extending far beyond the reach of visible stars. Within this halo, stars orbit the galactic center at speeds that defy the predictions of Newtonian physics if only visible matter were present. It is this discrepancy that first led scientists to infer its existence. Stars move too quickly and galaxies rotate too uniformly, unless something unseen is exerting gravitational influence. Dark matter, therefore, is not merely a passive background. It actively shapes the galaxy, dictating the motion of billions of stars across tens of thousands of light-years. Visualize drifting above the Milky Way, watching the stars spiral gracefully in their arms. What we perceive as order and symmetry is actually underpinned by dark matter, a hidden scaffolding that is invisible to all but the most sensitive instruments. It is not evenly distributed. It forms clumps and streams, subtly affecting the trajectories of stars and gas clouds. Entire structures of the galaxy, including the spiral arms and central bulge, owe their stability to this unseen component. Without dark matter, the Milky Way would lose its elegant shape and coherence, a beautiful swirl torn apart by the mechanics of motion. Dark matter also creates tension and mystery because it is fundamentally unknowable with current technology. Unlike gas or stars, we cannot measure it directly, We cannot observe it radiate and we cannot touch it. Its existence is inferred only through gravitational effects, computer simulations and careful observation of galactic dynamics. This means that nearly everything holding the galaxy together remains largely a mystery. It is a silent architect, omnipresent yet undetectable, a ghostly presence whose influence we feel but whose nature we cannot comprehend. The implications of dark matter are profound. It suggests that the universe is mostly composed of things we cannot see, and that the stars, planets, and galaxies we study are only the visible tip of an enormous, hidden structure. The Milky Way, magnificent as it appears, is more shadow than substance, a luminous surface shaped by an invisible skeleton. For humanity, this raises a humbling realization. Everything we know and can observe is dwarfed by an unseen majority, a reminder of how small our understanding remains in the grand cosmic context. Even within the halo of dark matter, tiny ripples exist, subtle gravitational variations that can shepherd stars into clusters, trigger bursts of star formation, or influence the paths of satellite galaxies orbiting the Milky Way. Dark matter is not inert. It is a dynamic, ever-present influence shaping the galaxy's evolution over billions of years. It is both a stabilizer and a force of subtle change, quietly dictating the motions of celestial objects that seem otherwise random to an observer on Earth. Emotionally, dark matter evokes both awe and unease. Awe at the scale and precision of a force that can hold together an entire galaxy, orchestrating the motion of billions of stars across vast distances. Unease at the fact that it is invisible, incomprehensible, and possibly more massive than all visible matter combined. The very foundation of the Milky Way rests on something we cannot directly study, a reminder of the fragility and uncertainty underlying even the most stable structures in the universe. As we trace the spiral arms and observe the stars orbiting the galactic center, it becomes clear that the luminous beauty of the Milky Way is inseparable from this invisible framework. Dark matter shapes the galaxy's destiny, influences its past, and controls the future paths of countless stars and planetary systems. It is a silent, omnipresent architect, both awe-inspiring and enigmatic, a reminder that what we see in the night sky is only a fraction of the truth. The presence of dark matter forces us to confront the limits of human perception and understanding. We exist on a tiny planet orbiting a modest star, within a galaxy whose shape, motion, and very existence depend on an invisible, unknowable force. It is humbling to realize that the structures we admire, the spiral arms, clusters, and nebulae, are not merely natural formations, but are held together by a shadowy entity that dominates the cosmic landscape. Dark matter is a silent testament to the universe's scale, mystery, and complexity, a hidden giant that defines the very stage on which the drama of the Milky Way unfolds. In this way, dark matter transforms our understanding of the galaxy from a simple collection of stars into a living, dynamic structure bound by an invisible, omnipresent hand. It is both terrifying and magnificent, a reminder that the cosmos contains far more than our senses can detect and far more than our minds can fully grasp. The Milky Way is not merely a city of light, it is a city held together by shadows, a luminous pattern suspended on a hidden skeleton of unimaginable scale and influence. Within the vast expanse of the Milky Way, stars are not solitary wanderers. They form intricate communities, clusters, and associations that move together through space like bustling neighborhoods in a sprawling cosmic city. These star clusters vary enormously in size, age, and composition, yet each reveals essential truths about the life and evolution of the galaxy. They are laboratories of creation and destruction, where stars are born, mature, and die under the influence of gravity, radiation, and unseen cosmic forces. For humans observing from Earth, they appear as sparkling points of light, but in reality, they are enormous gatherings of matter, energy, and history, stretching across dozens or even hundreds of light years. There are two primary types of star clusters: open clusters and globular clusters, each representing different stages and conditions of stellar evolution. Open clusters are relatively young, loosely bound collections of stars that formed from the same molecular cloud. They are scattered along the spiral arms of the galaxy, glowing with the blue-white light of hot, young stars. These clusters are dynamic and transient. Over tens of millions of years, the gravitational pull of the galaxy gradually disperses them, sending their stars drifting into the broader galactic population. Examples like the Pleiades or the Hyades, visible to the naked eye from Earth, illustrate the beauty and fragility of these stellar families. Within each cluster, stars interact gravitationally, influencing one another's orbits, triggering new stellar births, and even occasionally colliding in violent events that reshape the local environment. Globular clusters, in stark contrast, are ancient, densely packed spheres of stars, often containing hundreds of thousands or even millions of members. They orbit the galaxy in the halo, far above and below the plane of the disk, like ancient citadels surrounding a bustling city. These clusters are remarkably stable, bound together by mutual gravity, and have existed for more than 10 billion years, older than our Sun and even some of the spiral arms themselves. Observing them is like looking at a living fossil, a glimpse of the early Milky Way preserved in tightly packed stellar communities. Each globular cluster tells a story of survival and endurance, its stars quietly aging while the galaxy around them evolves and changes. The formation of these clusters is governed by immense, often violent processes. In the case of open clusters, vast molecular clouds collapse under gravity, compressing gas and dust until nuclear fusion ignites new stars. Supernova explosions within these clouds can trigger subsequent waves of star formation, while simultaneously scattering some material into interstellar space. Globular clusters formed under even more extreme conditions in the early galaxy, when gas was denser, more chaotic, and enriched with fewer heavy elements. Their formation required immense concentrations of matter, intense gravitational cohesion, and the passage of billions of years to stabilize. Star clusters also play a crucial role in shaping the larger galactic structure. Their combined gravitational influence can subtly affect the orbits of nearby stars, shepherding them into spiral arms or altering the density of interstellar gas. They serve as nurseries and archives simultaneously. Within their confines, new stars emerge, while ancient stars record the chemical history of the galaxy. By studying clusters, astronomers can trace the Milky Way's past, its periods of star formation, galactic collisions, and chemical evolution, revealing patterns invisible when observing individual stars alone. Traveling through a cluster, one would witness a scene of immense variety and energy. Young clusters radiate intense ultraviolet light from their hottest stars, ionizing surrounding gas and creating colorful nebulae. In globular clusters, countless red and yellow stars crowd together, their light blending into a dense, golden haze. Stellar interactions in these dense regions can produce exotic objects: blue stragglers that appear younger than their neighbors, pulsars that spin with extraordinary precision, and even binary systems destined to end in spectacular supernovae or merge into black holes. Each cluster is a microcosm of the galaxy, a miniature ecosystem of stars, radiation, and gravity, operating on scales that dwarf entire solar systems. Yet, even as clusters are monumental on a human scale, they underscore the insignificance of our place in the galaxy. The solar system is not part of any major cluster. It drifts in a relatively sparse region of the Orion Arm, isolated from the crowded stellar neighborhoods where dramatic interactions occur. From this perspective, the clusters are both awe-inspiring and intimidating, massive structures moving silently through space while our tiny solar system orbits unnoticed within the vast galactic suburbs. They remind us that the universe is organized on scales far beyond our daily comprehension, where entire families of stars live, age, and die together, indifferent to the small, fragile planet we call home. Clusters also evoke a sense of temporal depth. Open clusters dissolve over tens of millions of years, reminding us of the fleeting nature of most stellar communities. Globular clusters endure for billions of years, yet even they are not permanent. Tidal forces from the galaxy slowly strip stars away, gradually altering the cluster's shape and composition. Through these dynamics, we perceive a galaxy in motion, a system where matter is constantly redistributed, yet patterns of structure and order persist across incomprehensible spans of time. Emotionally, star clusters inspire both wonder and humility. They are places of intense creation and serene endurance, of violent interactions and timeless stability. They show us the sheer scale of the galaxy, the processes that govern star formation, and the hidden forces that maintain structure over eons. They also remind us of our fragility and transience. While entire clusters live and evolve over billions of years, human civilization exists for mere moments in comparison, a brief flicker within the vast theater of the Milky Way. By studying these clusters, astronomers unlock secrets of galactic evolution, star formation, and cosmic history. They reveal chemical compositions that trace the birth and death of stars, the collisions of galaxies, and the migration of stellar populations. They show us that the Milky Way is not a random scattering of stars, but a carefully orchestrated structure, with dense hubs, loose suburbs, and ancient citadels, each contributing to the overall harmony of the galaxy. In essence, star clusters are living archives of the Milky Way, carrying within them both the violent past and the ongoing story of stellar evolution. They illustrate the grandeur and scale of our galaxy while simultaneously highlighting the solitude of our solar system, drifting quietly through a comparatively sparse region. Within their radiant bounds, billions of stars participate in intricate gravitational dances, forming patterns, creating light, and leaving behind evidence of cosmic history, a vivid reminder of the immense, interconnected, and awe-inspiring nature of the universe we inhabit. Between the stars and clusters of the Milky Way lies a vast, almost imperceptible network of gas and dust known as the interstellar medium. This medium is the lifeblood of the galaxy, an invisible substance that both sustains and reshapes it over time. Though it is nearly empty by earthly standards, containing only a few atoms per cubic centimeter, its cumulative effect across tens of thousands of light-years is immense. The interstellar medium fills the spaces between stars, acting as both a cradle for new stellar life and a repository for the remnants of stars long dead. It is a cosmic tapestry of subtle energy and matter, a medium that shapes the evolution of the galaxy in ways both dramatic and silent. The interstellar medium is composed primarily of hydrogen and helium, the most abundant elements in the universe, mixed with trace amounts of heavier elements like carbon, oxygen, and iron. These materials exist in multiple phases: cold, dense molecular clouds where temperatures drop to just a few degrees above absolute zero, warmer, diffuse atomic gas that drifts across the galactic disk, and hot, ionized gas created by supernova explosions and energetic stellar winds. Each phase interacts with the others, forming a dynamic, ever-changing environment. Molecular clouds collapse under gravity to form stars, while supernova remnants inject energy back into the medium, heating it, stirring it, and dispersing elements forged in the hearts of dying stars. Picture drifting through a molecular cloud in the spiral arm of the Milky Way. The darkness is almost complete, punctuated only by the faint glow of distant stars filtered through thick veils of dust. Within this cloud, gravity gathers gas and dust into dense pockets, compressing matter until nuclear fusion ignites a newborn star. Surrounding it, disks of dust coalesce, eventually forming planets, asteroids, and comets. These clouds are the factories of the galaxy, the sites where the raw materials of planets and life are assembled. Each molecular cloud is a bustling workshop of creation, quiet and hidden from casual observation, yet essential to the ongoing story of the Milky Way. Beyond the molecular clouds, the warmer atomic and ionized gas forms an invisible web connecting different regions of the galaxy. Streams of gas flow along spiral arms, influenced by gravitational tides and the orbits of stars. Supernovae create shockwaves that ripple through this medium, compressing some regions and dispersing others. These processes regulate star formation, ensuring that the galaxy remains a dynamic system rather than a static collection of stars. In this way, the interstellar medium is both a mediator and a driver of galactic evolution, maintaining balance between creation and destruction on a scale beyond human comprehension. Dust particles within the interstellar medium, though tiny, play an outsized role. They absorb and scatter light, obscuring distant stars and shaping the visual appearance of the galaxy. These grains act as surfaces where chemical reactions occur, forming molecules critical to the development of planets and potentially life. Through their interaction with starlight, magnetic fields, and cosmic radiation, dust grains influence the temperature, density, and chemistry of the surrounding gas. Without these minute particles, the processes that govern star formation, planetary evolution, and even the appearance of the night sky would be fundamentally different. The interstellar medium is also a repository of history. Supernova explosions, stellar winds, and planetary nebulae deposit elements created in stars into the surrounding gas, enriching it with the building blocks of planets and life. These recycled materials drift through space, eventually forming new generations of stars and planetary systems. In this sense, the interstellar medium is a cosmic memory, carrying the chemical fingerprints of countless stars that have lived and died over billions of years. Every molecule of gas and dust tells a story of creation, destruction, and transformation, connecting past and future generations of celestial objects. This invisible network also contributes to the contrast and mystery of the galaxy. To human eyes, the Milky Way appears as a glowing band of stars, a beautiful, static image. Yet interwoven through this glittering field is the interstellar medium, shaping light, absorbing it, redirecting it, and creating shadowy lanes and dark voids. These regions obscure and reveal, creating dramatic contrasts that make the galaxy visually and scientifically compelling. Without the interstellar medium, the Milky Way would be a flat, featureless disk of stars. With it, the galaxy becomes a rich, textured landscape full of complexity and intrigue. Even in the sparsest regions, the interstellar medium is never truly absent. Between clusters, spiral arms, and the galactic halo, tenuous streams of gas stretch across light years, carrying momentum, energy, and matter. These streams interact subtly with stars and planets, altering trajectories over millions of years. The Milky Way is not simply a collection of stars. It is a living, breathing system in which even the emptiest regions are imbued with structure, energy, and purpose. The interstellar medium binds the galaxy together in ways invisible but undeniable, a silent architect shaping its past, present, and future. Emotionally, the interstellar medium evokes both awe and reflection. Awe at the scale and subtlety of the processes that govern the formation of stars, planets, and life. Reflection on the interconnectedness of all things. The atoms in our bodies were forged in stars, expelled into the interstellar medium, and eventually incorporated into the Earth. In this vast, nearly empty space, we can trace the origins of life and recognize the continuity of matter across billions of years and trillions of kilometers. The medium is a reminder of the galaxy's dynamism and the intimate connection between humanity and the cosmos. Ultimately, the interstellar medium is the connective tissue of the Milky Way, binding stars, clusters, and gas clouds into a coherent, evolving system. It is both a birthplace and a graveyard, a conduit of energy and matter, and a medium of memory that records the galaxy's history. Without it, the Milky Way would lose its structure, its rhythm, and much of its beauty. It is a silent, invisible presence, shaping the galaxy's fate while remaining largely hidden from view, a quiet force that defines the very environment in which the solar system drifts, and in which life on Earth ultimately emerged. The spiral arms of the Milky Way are among its most striking and dynamic features, vast swaths of stars, gas, and dust winding gracefully around the galactic center like immense cosmic ribbons. These arms are far from static. They are patterns of higher density that sweep through the galactic disk, compressing gas, triggering star formation, and orchestrating the movements of billions of stars. To the casual observer, they appear as luminous streaks across the night sky, their beauty captured in telescope images and artists' renderings. Yet these arms are not merely decorative, they are essential engines of the galaxy's life, governing the birth, evolution, and motion of stars, planetary systems, and clusters within their reach. The spiral arms are sites of intense stellar activity. As the density waves that define the arms sweep through the galaxy, they compress clouds of gas and dust, initiating gravitational collapse that gives birth to new stars. Within these clouds, newborn stars emerge in clusters, their ultraviolet light ionizing surrounding gas and creating nebulae that glow with vibrant colors. These regions are often crowded, chaotic, and luminous, in stark contrast to the relative emptiness of the spaces between the arms. In this sense, the spiral arms are not static structures but dynamic, moving environments, continually cycling gas and dust into stars and back into the interstellar medium through stellar winds and supernova explosions. Each spiral arm has its own character. Some are thick with bright, young stars and vibrant nebulae, pulsing with energy and radiance. Others are more diffuse, containing older stars, scattered gas, and remnants of past star formation. As one travels along an arm, the density of stars fluctuates, the color shifts from brilliant blue-white regions of youth to softer golden hues of older populations. These contrasts create a living, breathing galaxy, where beauty, violence, and creation coexist on scales that dwarf human comprehension. The spiral arms are both a visual spectacle and a physical mechanism, shaping the Milky Way structure while serving as the primary sites of star formation. The Sun itself resides in a relatively minor arm, the Orion Arm, sometimes called the Orion Spur. It is a modest segment of the galaxy's larger structure, situated between the more prominent Sagittarius and Perseus arms. Within this arm, the Sun and its solar system drift through regions of varying stellar density, encountering clouds of gas, occasional star clusters, and interstellar dust. This position is relatively calm compared to the dense inner arms or the galactic core, providing stability that may have been crucial for the emergence and persistence of life on Earth. Yet even here, motion and interaction are constant. Clouds of gas drift, stars move in their orbits, and the Sun itself travels at hundreds of kilometers per second along its path, weaving through the arm like a boat on a cosmic river. The spiral arms are also sites of cosmic contrast. While some regions blaze with the birth of massive stars that will live fast and die young in brilliant supernovae, other regions are quieter, hosting ancient stars that have persisted for billions of years. These juxtapositions between creation and endurance, chaos and stability, illuminate the galaxy's narrative on scales far beyond human life. The interplay of light and shadow, activity and calm, is what gives the Milky Way its structure and its aesthetic majesty. Without these arms, the galaxy would lack its organized, spiral form, and the processes that drive the ongoing cycle of stellar evolution would be scattered and inefficient. On an even grander scale, spiral arms influence the motion of stars and planetary systems. As the density waves pass through the galactic disk, stars slow slightly as they enter denser regions and speed up as they exit, creating orbital resonances that shape stellar trajectories over millions of years. Gas clouds compressed by these waves form new stars, which eventually drift out of the arm into interarm regions. The arms are not solid entities, they are moving patterns like the wake of a ship cutting through water, but their influence is profound, governing the distribution and evolution of matter across the galaxy. Within the arms, supernovae inject energy and heavy elements into the interstellar medium, seeding future generations of stars and planetary systems. Every atom of carbon, oxygen, iron, and other essential elements was forged in the heart of a dying star, and the spiral arms are the places where these materials are returned to the galactic ecosystem. These processes create a feedback loop. Stars form, evolve, die, and enrich the medium, which collapses again to form new stars. It is a cycle of creation and destruction on a scale that spans millions of years, yet it unfolds continuously, quietly shaping the galaxy even as we gaze at it from our small corner of the Orion Arm. Emotionally, the spiral arms evoke awe and a sense of connection. They are tangible evidence of motion, structure, and life within the galaxy, stretching across tens of thousands of light-years and hosting processes that ultimately give rise to planets and potentially life. They demonstrate both the immense scale of the Milky Way and the intricate order hidden within that scale. Even as our solar system drifts through a quiet portion of one arm, the arms themselves remind us that we are part of a larger, dynamic system where every star, gas cloud, and dust lane plays a role in a cosmic dance billions of years in the making. In essence, the spiral arms are both the skeleton and the heartbeat of the Milky Way. They organize matter, drive the birth of stars, sculpt nebulae, and regulate motion, all while producing the luminous beauty that has inspired generations of astronomers and dreamers. They are patterns of life and motion, guiding the evolution of the galaxy on a scale that defies imagination. Through their existence, we see the Milky Way not as a static backdrop, but as a vibrant, interconnected, and endlessly dynamic system. An enormous, living structure in which even our modest solar system participates, quietly drifting through a river of stars, dust, and cosmic energy. The galactic core of the Milky Way is a realm of extremes, a seething, densely packed heart where the familiar rules of cosmic calm give way to turbulence, heat, and gravitational intensity. Unlike the serene suburbs where our sun drifts, the core is crowded with millions of stars within just a few light-years, swirling gas clouds heated to millions of degrees, and compact stellar remnants packed into a region smaller than 1/100th of the galaxy's diameter. Imagine standing at the edge of this domain. The night sky would be blindingly bright, every direction filled with stars and energetic phenomena, a chaotic hive of cosmic activity unlike anything in the quiet Orion Arm where Earth resides. The galactic core is both a furnace of creation and a zone of destruction, a place where the laws of physics are on full display, unfiltered and uncompromising. At the very center of this tumult lies Sagittarius A*, a supermassive black hole with a mass exceeding 4 million times that of our Sun. Though invisible directly, its presence dominates the orbits of nearby stars, bending spacetime and accelerating matter to velocities approaching the speed of light. Stars near this gravitational titan trace intricate hyperbolic or elliptical paths, dancing in ways that can take decades or centuries to complete. Some stars plunge perilously close, their atmospheres stripped away by intense tidal forces, while others are flung outward, ejected from the core entirely. Sagittarius A* is a silent architect of chaos, a massive anchor around which the heart of the galaxy swirls, dictating motion, energy distribution, and the dynamics of the innermost stellar population. The core is also the site of intense star formation. Gas clouds, compressed by gravitational interactions and shockwaves from nearby supernovae, collapse to form new generations of stars at a rate far higher than in the galactic disk. These newborn stars are often massive, luminous, and short-lived, burning bright and dying young in spectacular supernova explosions. Each explosion injects energy, radiation, and heavy elements into the surrounding medium, influencing subsequent star formation and enriching the galactic center with the raw materials for planets and complex chemistry. This cycle of creation and destruction is amplified by the crowded environment. Stars are close enough to interact, collide, or strip material from one another, creating exotic systems that would be impossible in the quiet suburbs of the galaxy. Cosmic radiation and high-energy particles permeate the core, bathing the environment in X-rays, gamma rays, and charged particles. Supernova remnants, pulsars, and compact binary systems contribute to an intense background of energy, making this region extraordinarily hostile to life as we know it. If our solar system were located here, the Earth's atmosphere and magnetic field would be continually bombarded by lethal radiation, sterilizing the planet repeatedly. The contrast with our own relatively safe position in the Orion Arm is stark. What is tranquil and conducive to life on the galactic outskirts is deadly and chaotic in the core. This juxtaposition highlights the delicate balance of location and circumstance that has allowed life to flourish on Earth. The core is also a place where stellar evolution accelerates. Massive stars, forming and dying within mere millions of years, dominate the landscape, while older, lower-mass stars crowd into dense neighborhoods. Stellar collisions and mergers are more common, producing unusual objects such as blue stragglers, stars that appear younger than their neighbors, and compact binaries that can eventually produce gravitational waves detectable across the galaxy. The gravitational interactions are constant, reshaping orbits and redistributing energy in a high-stakes ballet of celestial dynamics. Every object in the core is both a participant and a witness to processes that are rare elsewhere, giving the region an intensity unmatched in the galactic disk or halo. Interstellar gas and dust in the core are heated to extreme temperatures, emitting radiation across the electromagnetic spectrum. Infrared telescopes reveal clouds of hot dust swirling around young stars, while radio telescopes detect massive clouds of ionized gas orbiting close to the black hole. These clouds are in constant motion, compressed and stretched by gravity, colliding and fragmenting, sometimes forming new stars or feeding the central black hole. Sagittarius A** itself occasionally accretes material, triggering flares of X-ray and radio emission that ripple through the surrounding environment. The core is thus a zone where matter is constantly recycled, energy is in perpetual motion, and the rules of life, death, and transformation are writ large on cosmic scales. Emotionally, the galactic core evokes both awe and dread. Awe at the raw power and dynamism of a region where millions of stars interact under the influence of a supermassive black hole. Dread at the inhospitable conditions, the immense radiation, and the violent interactions that make survival for any life form improbable. It is a realm of extremes, a laboratory where physics is on full display and the universe's most intense forces are concentrated. For astronomers and dreamers alike, it is both terrifying and mesmerizing, a reminder of the vast range of environments the galaxy contains, from serene starry suburbs to incandescent, chaotic hearts. From a narrative perspective, the core provides a striking contrast to the solar system's quiet neighborhood. While Earth orbits a relatively stable, unremarkable star, the center of the galaxy churns with energy, danger, and gravitational drama. This contrast deepens the sense of human fragility and the fortuitous circumstances that have allowed life to persist. It is a reminder that the Milky Way is not uniform. Regions vary from calm to violent, from sparse to crowded, from cold voids to furnace-like densities. Every journey through the galaxy reveals extremes, but the core exemplifies them in concentrated, overwhelming form. Ultimately, the galactic core is the beating heart of the Milky Way, a region where creation and destruction coexist in a relentless, magnificent cycle. Stars are born, live brilliant lives, and die, feeding the next generation and sustaining the energetic ecosystem of the center. Gravity dominates, shaping orbits, interactions, and energy flows, while the central black hole commands the stage with silent authority. The core is a testament to the extremes of nature and the sheer scale of cosmic processes, offering a window into the forces that have shaped the galaxy from its earliest moments and continue to drive its evolution today. It is a place of wonder, danger, and profound significance, a reminder of both the majesty and the indifference of the universe. Between the galactic core and the spiral arms lies a fascinating and often overlooked region known as the galactic bulge. This dense, roughly spherical concentration of stars surrounds the Milky Way's center, bridging the intense chaos of the core with the relatively calm neighborhoods of the disk. Unlike the well-defined spiral arms or the empty halo, the bulge is a crowded, ancient stellar city, home to a mixture of old, evolved stars and younger populations formed from gas funneled inward by gravitational forces. Imagine drifting through this region. The sky is ablaze with countless stars, their light overlapping and blending into a luminous haze, punctuated by nebulae, clusters, and the occasional dark lane of dust, creating a complex, textured environment that is both visually stunning and dynamically intriguing. The stars in the bulge are predominantly older than those in the disk, relics from the galaxy's early history. Red giants, aging in the final stages of stellar evolution, dominate the population, casting a warm golden glow across the region. Their light mingles with that of younger stars, forming a tapestry that speaks to billions of years of galactic evolution. Many of these stars are metal-rich compared to the halo, enriched over countless generations of supernovae that have recycled heavy elements back into the interstellar medium. Studying the bulge provides astronomers with a living record of the Milky Way's formation, a fossilized core of history wrapped around the energetic heart of the galaxy. The bulge is not merely a static collection of stars, it is a dynamic, rotating structure, shaped by the gravitational interplay between the core, the disk, and the spiral arms. Within it, stars follow complex orbits, some moving in elongated, bar-shaped patterns that create the galaxy's central bar, a feature visible in infrared observations. Gas clouds in the bulge are compressed, heated, and occasionally triggered into star formation, producing pockets of activity amid the older stellar population. These interactions create a delicate balance between stability and motion. The bulge maintains its overall structure while constantly evolving on timescales of millions of years, a living testament to the galaxy's capacity for both order and change. Embedded within the bulge are globular clusters and dense stellar associations, remnants of the Milky Way's formative years. These clusters act as anchors, gravitationally binding regions of stars together and influencing nearby orbits. Their presence highlights the bulge's layered complexity. It is not a uniform, homogeneous sphere but a rich, three-dimensional environment shaped by dynamics, history, and ongoing stellar evolution. Some of these clusters contain ancient stars nearly as old as the universe itself, their metallicity and chemical composition providing clues to the early processes that built the galaxy. Within the bulge, one can witness the past and present coexisting in a dense, intricate dance. Interstellar gas and dust within the bulge add another layer of complexity and drama. Though much of the material has been consumed by successive generations of stars, clouds of gas still drift through the region, occasionally compressed into new stars or feeding the central black hole. Infrared observations reveal filaments of warm dust intertwined with bright stellar light, while radio telescopes detect swirling clouds of molecular gas moving in intricate high-velocity orbits. These clouds are not passive. They interact with stars, supernova shockwaves, and magnetic fields, creating a dynamic environment where matter is continually recycled and reshaped. The bulge is thus a bridge between the serene starry outskirts and the violent core, a region where both the past and present converge. The bulge's density creates unique gravitational effects. Stars are packed much more tightly than in the disk, leading to frequent interactions and occasional close encounters. Binary systems, stellar mergers, and gravitational perturbations occur more often here than in the galaxy's suburbs, resulting in unusual stellar phenomena, exotic remnants, and high-energy emissions. The combination of density, motion, and history makes the bulge a laboratory for understanding stellar evolution, galactic dynamics, and the complex feedback loops that govern the Milky Way's growth. It is a region of concentrated learning for astronomers and a striking example of the galaxy's structural diversity. Emotionally, the bulge evokes awe, nostalgia, and contemplation. Awe at the sheer number of stars crowded into a relatively small volume, each a potential solar system, each a repository of cosmic history. Nostalgia for the early Milky Way, as the bulge preserves stars formed in the galaxy's infancy, a living memory of ancient processes that shaped the spiral arms and the disk. Contemplation arises from realizing that the solar system drifts far from this dense environment, in a quiet arm, isolated from the gravitational intensity and stellar crowding of the bulge. The contrast between the dense, energetic core and the calm suburbs underscores both our vulnerability and our fortuitous position in the galaxy. The bulge also demonstrates the importance of scale and perspective. From Earth, we perceive the Milky Way as a faint band across the sky, but within the bulge, stars are packed so densely that the night sky would blaze with light, a ceaseless shimmer of stellar energy. It is a reminder that our perception of the galaxy is limited, filtered by distance and obscured by intervening dust, and that reality on local scales can be unimaginably more intense and complex than what we observe from afar. Ultimately, the galactic bulge is a transitional region, both structurally and narratively, linking the frenetic high-energy core to the calmer, sprawling disk. It preserves the galaxy's ancient history while nurturing pockets of ongoing activity, balancing order and chaos in a dynamic, evolving environment. The bulge is a living archive, a luminous bridge, and a theater of gravitational interplay, a place where the Milky Way's past, present, and future converge. Within its densely packed stars, swirling dust, and orbiting clusters, the galaxy reveals both its complexity and continuity, offering insight into the processes that have shaped our cosmic home and the forces that continue to govern its evolution. The galactic halo is one of the Milky Way's most mysterious and ethereal components, a vast, nearly invisible sphere that envelopes the luminous disk and bulge, stretching tens of thousands of light-years above and below the galactic plane. Unlike the densely packed regions closer to the center, the halo is sparsely populated, a ghostly realm where stars, globular clusters, and dark matter drift silently in a vast, cold expanse. From Earth, this region is mostly hidden, detectable only through careful observations of ancient stars and the motions of globular clusters. Yet the halo is critical to the galaxy's structure and evolution, a hidden scaffold that binds everything together while telling the story of the Milky Way's formation and growth over billions of years. The stars in the halo are ancient, often older than the Sun by billions of years, relics from the early universe and the Milky Way's formative epochs. They are predominantly low-metallicity stars, composed mostly of hydrogen and helium, with only trace amounts of heavier elements. Their simplicity reflects the primitive conditions of their birth, long before the galaxy became enriched by successive generations of supernovae. These halo stars move in highly elliptical and sometimes inclined orbits, wandering far above and below the galactic plane, their paths influenced by both the gravitational pull of the visible disk and the invisible presence of dark matter. Unlike the orderly motion of stars in the disk, halo stars trace chaotic, wandering paths, a cosmic memory of ancient galactic events. Embedded within the halo are globular clusters, tightly bound spheres of tens of thousands to millions of stars, some of the oldest objects in the galaxy. These clusters orbit the Milky Way in elongated, often inclined trajectories, acting as sentinels of the halo's history. Their composition provides astronomers with a window into the early chemical makeup of the galaxy, while their orbits reveal the gravitational influence of both visible and dark matter. These ancient clusters are relics of a turbulent youth, surviving mergers, tidal forces, and the gradual evolution of the galactic disk. Each cluster is a compact archive of stellar evolution, a microcosm of the processes that have shaped the Milky Way over billions of years. The halo also contains streams of stars, remnants of dwarf galaxies and smaller star clusters that were gravitationally disrupted and absorbed into the Milky Way over cosmic time. These stellar streams trace the galaxy's cannibalistic history, evidence that the Milky Way grew not solely through internal processes but by accreting smaller galaxies in a slow, dramatic cosmic dance. Observing these streams allows scientists to reconstruct the past interactions and mergers that built the halo, revealing a history of violence, survival, and transformation on scales far beyond human comprehension. Each wandering star in the halo carries the story of a galaxy long consumed, a fragment of history orbiting silently at the edge of visibility. Dark matter dominates the halo's mass, far outweighing the stars and clusters embedded within it. This invisible component forms a spherical cocoon around the galaxy, its gravitational pull essential for maintaining the Milky Way structure. Without the halo's dark matter, the rotational speeds of stars in the disk would be inconsistent with the galaxy's observed mass distribution, and the Milky Way could not hold itself together. The halo is thus both a visible and invisible presence. Stars and clusters trace its form, while dark matter provides the underlying framework. It is a region where what is unseen is far more influential than what is seen, a reminder of the hidden forces shaping the cosmos. Interstellar gas in the halo is sparse, almost negligible compared to the disk, yet it carries important clues about galactic evolution. Some of this gas originates from ancient outflows driven by supernovae and stellar winds in the disk, while other portions are remnants of accreted galaxies, enriched with metals from previous generations of stars. This tenuous material slowly circulates through the halo, cooling, mixing, and sometimes falling back into the disk to fuel new star formation. Though largely invisible, it plays a subtle but critical role in the ongoing life cycle of the Milky Way. Emotionally, the halo evokes a sense of isolation, awe, and perspective. It is a realm of extremes: vast distances, sparse populations, and ancient stars drifting silently through space. From within the disk, the halo seems almost intangible, yet it is indispensable, quietly governing the motions of stars, clusters, and the galaxy itself. Its sparse beauty and ghostly character inspire contemplation, reminding us that much of the Milky Way exists beyond our immediate perception, in regions that are ancient, quiet, and unseen. The halo's vast emptiness highlights the fragility and significance of the solar system's position in the galactic suburbs, a tiny oasis of relative safety and density. The halo also serves as a bridge between the visible and invisible, the past and present. Its stars and clusters preserve the Milky Way's ancient history, while dark matter shapes its future evolution. Its streams and relics reveal the galaxy's violent formative processes, showing that even the quietest regions are products of dramatic cosmic events. By studying the halo, astronomers can trace the galaxy's growth, understand the distribution of mass, and probe the nature of dark matter itself, linking observation with theory in a quest to comprehend the Milky Way as a whole. Ultimately, the galactic halo is both a boundary and a foundation. It is the edge of the visible Milky Way, yet it supports the entire structure, providing mass, stability, and historical context. Its ancient stars, globular clusters, and stellar streams offer a living record of the galaxy's violent youth, while its dark matter cocoon dictates the future paths of billions of stars. The halo embodies mystery and majesty, isolation and influence, reminding us that the galaxy is far more than what meets the eye, and that even in apparent emptiness, there is structure, history, and unseen power guiding the Milky Way through cosmic time. Cosmic collisions are among the most dramatic and transformative events in the life of the Milky Way, shaping its structure, fueling star formation, and rewriting its history on scales that dwarf human imagination. Galaxies are not isolated islands drifting silently in space. They are social entities bound by gravity, constantly interacting, merging, and sometimes cannibalizing one another in slow-motion collisions that unfold over hundreds of millions or even billions of years. The Milky Way is no exception. Its current form is the product of countless past encounters with smaller galaxies, dwarf companions, and globular clusters, each leaving behind streams of stars, bursts of star formation, and subtle distortions in the galactic disk that persist for eons. One of the most striking consequences of these collisions is the formation of stellar streams, elongated ribbons of stars torn from disrupted galaxies or clusters as they fall into the Milky Way's gravitational embrace. These streams trace graceful arcs across the sky, invisible to the naked eye but detectable with sensitive telescopes and careful observations. Each stream is a relic of a past encounter, a visible record of violence, assimilation, and cosmic recycling. They are silent witnesses to events that took place hundreds of millions of years ago, their stars moving inexorably along paths determined by the galaxy's gravity, carrying with them the chemical signatures and histories of their original homes. Collisions and mergers also drive intense star formation, particularly in regions where gas clouds are compressed and shocked. When two galaxies interact, tidal forces and gravitational disturbances trigger the collapse of molecular clouds, igniting waves of stellar birth. Massive stars, forming in these regions, live short, brilliant lives, often ending in supernova explosions that enrich the surrounding medium with heavy elements. Over time, these processes can dramatically alter the chemical composition, density, and structure of the galactic disk. The Milky Way spiral arms, star clusters, and even the central bulge bear the imprint of countless such interactions, each event layering new complexity onto the galaxy's evolution. Perhaps the most famous ongoing collision involves the Milky Way and the Andromeda Galaxy, our massive neighbor located roughly 2.5 million light-years away. Gravitational attraction is drawing the two galaxies toward each other at hundreds of kilometers per second, a cosmic dance that will culminate in a colossal merger billions of years from now. As the galaxies approach, tidal forces will stretch and distort their disks, creating bridges and tails of stars, gas, and dust. Star formation will surge in compressed regions, while supermassive black holes at each galactic center may eventually merge, releasing titanic bursts of energy in the form of gravitational waves. This impending collision is a vivid example of the dynamic, ever-changing nature of galaxies, highlighting that the Milky Way is not static but a participant in a grand, ongoing cosmic story. Smaller, more frequent interactions have also left their mark. The Milky Way has accreted numerous dwarf galaxies over its history, including the Sagittarius dwarf and the Gaia Enceladus remnant, each contributing stars, gas, and dark matter to the galactic halo. These mergers leave subtle signatures, streams of stars orbiting at odd angles, variations in metallicity within different regions of the galaxy, and distortions in the disk and bulge. By studying these features, astronomers can reconstruct the Milky Way's complex assembly history, tracing its growth from a nascent collection of gas clouds and small stellar systems to the majestic spiral galaxy we see today. Cosmic collisions also highlight the interplay between order and chaos. While they are violent events, the long timescales involved allow new structures to emerge and stabilize. Stellar orbits, once perturbed, gradually settle into new patterns, spiral arms are reshaped, and clusters are redistributed. The galaxy absorbs these events, incorporating them into its ongoing evolution rather than being destroyed outright. In this sense, collisions are both destructive and creative, simultaneously tearing apart and building anew, illustrating the duality that defines much of cosmic evolution. Emotionally, the concept of galactic collisions evokes awe and humility. Awe at the sheer scale and energy involved, where billions of stars, vast clouds of gas and immense dark matter halos interact over incomprehensible distances. Humility in realizing that the solar system, though small and relatively isolated, will one day be swept along by forces far greater than itself, participating passively in a drama that has played out countless times in the universe. Collisions remind us that even galaxies, seemingly stable from our vantage point, are transient, evolving structures shaped by forces that operate on timescales far beyond human experience. The science of these interactions also provides profound insight into the Milky Way's past and future. By mapping stellar streams, modeling gravitational interactions, and observing star formation triggered by mergers, astronomers can decode the galaxy's life story, predicting how it will continue to change. Collisions are not random acts. They follow the universal laws of gravity and motion, yet their outcomes are unpredictable in detail, producing unique and sometimes chaotic results. This combination of predictability and unpredictability makes galactic collisions both scientifically fascinating and narratively compelling, a natural illustration of contrast and tension in cosmic storytelling. Ultimately, cosmic collisions reveal the Milky Way as a living, evolving entity, a galaxy shaped by interaction, assimilation, and transformation. Each encounter, whether with a dwarf galaxy or a future merger with Andromeda, leaves lasting imprints, guiding the distribution of stars, gas, and dark matter while fueling the cycle of creation and destruction that defines the galaxy. These events underscore that the universe is dynamic and interconnected, where even immense, seemingly immutable structures are subject to change. In the Milky Way, every star, stream, and cluster is a participant in this grand cosmic choreography, reminding us that motion, transformation, and interconnection are fundamental to the story of our galaxy. Dark matter is one of the most enigmatic and fundamental components of the Milky Way, a mysterious substance that neither emits nor absorbs light, yet exerts a profound gravitational influence over the galaxy. Though invisible to telescopes, dark matter outweighs all the stars, gas, and dust combined, forming an immense, roughly spherical halo that envelopes the Milky Way and dictates the motions of its visible components. Without this hidden mass, the galaxy would not hold together. Stars in the outer disk would escape into intergalactic space, spiral arms would unravel, and the overall structure of the Milky Way would collapse. Dark matter is the silent architect of the galaxy, providing the unseen scaffolding upon which all visible structures are built. The presence of dark matter is inferred from its gravitational effects. Observations reveal that stars in the outer regions of the disk rotate far faster than expected based solely on visible mass. This discrepancy implies an additional, invisible source of gravity, a massive halo of dark matter extending well beyond the luminous components of the galaxy. The halo is not uniform. Simulations suggest it is clumpy, with concentrations of dark matter influencing the formation of stars, clusters, and galactic substructures. These clumps may act as seeds for star formation or subtly perturb stellar orbits, demonstrating that even an invisible substance can profoundly shape the evolution of a galaxy. Dark matter's composition remains one of astronomy's deepest mysteries. Hypotheses abound, from weakly interacting massive particles, WIMPs, to ultralight axions, yet none have been directly detected. Unlike ordinary matter, dark matter does not interact electromagnetically, meaning it cannot form stars, planets, or chemical structures. It exists as a diffuse, unseen presence, detectable only through the gravitational footprints it leaves behind. In the Milky Way, this means that the solar system, spiral arms, clusters, and even the galactic core are embedded within a vast, invisible ocean of matter that defines the galaxy's dynamics and stability. The influence of dark matter extends beyond motion. By providing additional gravitational binding, it stabilizes the galactic disk against disruptive forces, such as tidal interactions with satellite galaxies or internal instabilities that might otherwise distort the spiral arms. It also helps maintain the orbits of globular clusters, halo stars, and stellar streams, allowing these structures to persist for billions of years. Without dark matter, the Milky Way would be a radically different galaxy. more fragile, less organized, and incapable of sustaining the environments necessary for star formation and ultimately life. Dark matter also plays a role in the Milky Way's cosmic history. During the galaxy's formation, its gravitational well, shaped largely by dark matter, attracted gas, dust, and smaller protogalaxies, guiding the accretion processes that built the spiral disk, bulge, and halo. Mergers and interactions with dwarf galaxies were influenced by the invisible mass surrounding the Milky Way, shaping the orbits of incoming stars and the distribution of tidal streams. In essence, dark matter has not only held the galaxy together but has actively guided its assembly over billions of years, influencing where stars form, how they move, and how the galaxy grows. The contrast between the invisible and the visible, the known and the unknown, makes dark matter a profoundly intriguing concept. While telescopes reveal the dazzling splendor of the Milky Way, the glittering disk, glowing nebulae, spiral arms, and dense core, dark matter lurks unseen, shaping all of it silently and persistently. It is a reminder that appearances can be deceiving. The galaxy's majesty depends as much on what we cannot see as on what we can observe. This invisible presence introduces a sense of cosmic mystery, highlighting the limits of human perception and the hidden complexities of the universe. Emotionally, dark matter evokes awe, humility, and curiosity. Awe at the sheer scale and influence of something we cannot perceive directly, yet which dominates the structure and evolution of the Milky Way. Humility in realizing how little we truly understand about the forces that govern our cosmic environment. Curiosity in driving scientists and observers to explore, model, and detect the elusive particles that make up this invisible halo. Dark matter embodies both the power and the mystery of the cosmos, a reminder that the universe is filled with phenomena far beyond ordinary experience, shaping reality in ways that are subtle, profound, and essential. From a structural perspective, dark matter connects the Milky Way to the larger cosmic web. Galaxies are not isolated. They exist within filaments and voids shaped by dark matter on intergalactic scales. The Milky Way's halo merges with the extended dark matter structures of the local group, influencing the approach of Andromeda and other nearby galaxies. This unseen connectivity emphasizes the galaxy's embeddedness within a broader cosmic network, highlighting that even our home system is part of a vast, interlinked structure dominated by forces beyond direct perception. Ultimately, dark matter is both the foundation and the mystery of the Milky Way. It anchors the stars, stabilizes the spiral arms, preserves clusters, and influences galactic evolution, yet remains unseen, intangible, and largely unexplained. It embodies the duality of the universe, invisible yet essential, mysterious yet determinative, subtle yet powerful. Without dark matter, the Milky Way as we know it could not exist. With it, the galaxy is a coherent, evolving structure, a masterpiece of cosmic architecture, silently shaped by the unseen hand of matter that neither shines nor dims, but guides the motions and fate of billions of stars across billions of years. Cosmic time is the invisible thread that weaves together the Milky Way's past, present, and future, stretching across billions of years in a scale so vast that human lifetimes are mere flickers in comparison. Unlike the familiar cycles of day and night or the changing seasons on Earth, cosmic time operates on a scale where stars are born, live, and die over millions or billions of years, galaxies collide and merge over eons, and matter drifts through the interstellar medium almost imperceptibly. Within this framework, the Milky Way itself is a dynamic entity, its spiral arms, bulge, halo, and core constantly evolving, yet all unfolding according to the inexorable march of time. To understand the galaxy is to grasp the rhythms of a history that predates the Earth and will continue long after the solar system fades. Stars serve as living clocks in this vast timeline. Massive stars, burning through their nuclear fuel at incredible rates, live fast and die young, exploding as supernovae within mere millions of years. These explosions inject energy and heavy elements into the surrounding interstellar medium, shaping the next generation of stars in a continuous, cascading cycle. In contrast, smaller stars like the Sun burn slowly, living for billions of years, providing stability and continuity amid the galaxy's constant change. The juxtaposition of short-lived brilliance and enduring persistence illustrates how cosmic time encompasses extremes, creating a complex, layered rhythm that governs the life cycles of all stellar objects. The formation of the Milky Way itself is a story written in cosmic time. Billions of years ago, primordial gas clouds collapsed under gravity, coalescing into the first stars and proto-galaxies. These early systems merged and accreted over time, forming the galactic disk, bulge, and halo that we observe today. Each merger, each star formation episode, Each gravitational interaction is a chapter in a narrative that spans epochs, a story that is simultaneously violent and creative. By studying the chemical composition, orbits, and ages of stars, astronomers can reconstruct this chronology, reading the history of the Milky Way as though it were an ancient manuscript, written in the language of light, motion, and matter. On a larger scale, cosmic time governs the Milky Way's interactions with its environment. Satellite galaxies, stellar streams, and even the future collision with Andromeda all unfold over hundreds of millions to billions of years. Tidal forces slowly distort structures, gas clouds gradually collapse into stars, and dark matter halos guide the motion of stars and clusters over incomprehensible distances. Time in the galaxy is cumulative, measured not in seconds or centuries, but in processes so prolonged that change appears both inevitable and imperceptible. For the solar system, this means that while our immediate neighborhood feels stable, the galaxy itself is a dynamic, ever-shifting tapestry shaped by the slow, relentless passage of cosmic epochs. Cosmic time also introduces perspective and contrast. While the human experience is brief, the Milky Way has been evolving for over 13 billion years and will continue for billions more. Stars that formed in the galaxy's early days may have already died, leaving behind remnants such as white dwarfs, neutron stars, or black holes, while new stars continue to ignite in molecular clouds. Planetary systems, including Earth, are transient players on this grand stage, mere moments in the galaxy's long narrative. This awareness evokes humility, emphasizing that while life on Earth is precious and immediate, it is but a brief interlude in a history that spans eons and a future that stretches into the incomprehensible. Observing the galaxy is, in essence, looking back in time. Light from distant stars and nebulae takes thousands, tens of thousands, or even millions of years to reach us, meaning we see these objects as they were long ago, not as they are now. This natural time machine allows astronomers to study different epochs simultaneously, comparing ancient stars in the halo with young star-forming regions in the spiral arms. Cosmic time is thus encoded in every photon, every spectral line, and every orbital motion, allowing us to piece together the story of the Milky Way with both precision and wonder. Each observation is a glimpse into the galaxy's temporal depth, a reminder that the universe is ancient, vast, and continuously unfolding. The passage of cosmic time also shapes the chemical evolution of the galaxy. Heavy elements synthesized in the cores of stars and expelled in supernovae accumulate over billions of years, enriching successive generations of stars and planetary systems. This enrichment provides the ingredients for rocky planets, complex chemistry, and, ultimately, the potential for life. In this sense, time is not just a measure of change, it is the medium through which complexity and diversity arise. Without billions of years of gradual evolution, the galaxy would lack the structures and materials that make Earth and its biosphere possible. Emotionally, cosmic time inspires awe, introspection, and a sense of connectedness. Awe at the scale and duration of processes that shape galaxies, from star formation to mergers, from the slow drift of dark matter to the relentless pull of gravity. Introspection in recognizing the fleeting nature of human life against the backdrop of billions of years, and a sense of continuity in realizing that the matter making up our bodies was once part of ancient stars, recycled through countless cycles of cosmic creation and destruction. Cosmic time transforms the Milky Way from a static, beautiful backdrop into a dynamic, living narrative in which all matter participates and evolves. Ultimately, cosmic time is the framework that gives meaning to the Milky Way's structure, motion, and evolution. It links the past, present, and future, connecting ancient stars to newborn ones, shaping chemical composition, guiding gravitational interactions, and dictating the cycles of birth and death that define the galaxy. Time transforms space into story, turning gas clouds, star clusters, spiral arms, and the galactic core into chapters in a narrative that unfolds over billions of years. In understanding cosmic time, we grasp not only the scale of the Milky Way but also our place within it, appreciating that the galaxy, and everything within it, exists as part of an unbroken, awe-inspiring continuum that stretches across the eons. The future of the Milky Way is a story written in the language of gravity, motion, and cosmic inevitability, a tale that will unfold over billions of years long after the present moment has passed. While the galaxy may seem stable to human eyes, its evolution is far from complete. Stars are born and die, spiral arms shift and twist, and the vast halo of dark matter silently orchestrates the orbits of billions of stars. The Milky Way is a dynamic, evolving system, and understanding its future requires both imagination and rigorous science, combining observations, simulations, and theoretical models to glimpse what lies ahead for our galactic home. One of the most monumental events on the horizon is the anticipated collision with the Andromeda Galaxy, a neighbor of comparable size located approximately 2.5 million light-years away. Gravitational attraction is drawing the two galaxies together at speeds exceeding 100 kilometers per second, setting the stage for a titanic encounter billions of years from now. As the galaxies approach, tidal forces will distort their disks, stretching stars and gas into enormous bridges and tails that connect the two spirals. Dense molecular clouds will collide, triggering waves of star formation that light up the galaxies in brilliant bursts of new stellar life. In this cosmic ballet, destruction and creation will be intertwined, highlighting the duality inherent in galactic evolution. Over the course of this merger, the supermassive black holes at the centers of both galaxies are likely to spiral toward one another, eventually coalescing in a cataclysmic event that will release immense gravitational waves. These waves will ripple across the fabric of space-time, carrying energy far beyond the confines of the Milky Way and Andromeda. The central regions of the merged galaxy will become chaotic, with stars flung into new orbits, gas clouds compressed into dense clusters, and new stellar nurseries ignited by shockwaves. This event will transform both galaxies profoundly, blending their structures into a single, more massive elliptical galaxy that will dominate the local group for billions of years to come. Even beyond this dramatic encounter, the Milky Way's evolution continues in subtler ways. Stars in the disk gradually drift from their birthplaces, altering the spiral structure over time. Supernovae continue to enrich the interstellar medium with heavy elements, preparing the environment for new generations of stars and planets. The halo, both visible and dominated by dark matter, continues to exert gravitational influence, guiding the orbits of satellite galaxies, stellar streams, and globular clusters. These ongoing processes remind us that the Milky Way is never static. It is in a state of perpetual motion, its structure evolving on timescales that dwarf human perception. Cosmic timescales also mean that the solar system, along with Earth, will experience changes even within this dynamic galaxy. Over the next several billion years, the Sun will gradually exhaust its hydrogen fuel, expanding into a red giant before shedding its outer layers and leaving behind a white dwarf. Planetary orbits may shift subtly under the influence of passing stars or gravitational perturbations, and the environment of the solar system will evolve in ways both predictable and uncertain. Our immediate cosmic neighborhood is intertwined with the galaxy's broader evolution, illustrating that local and global dynamics are inseparable when considering the Milky Way's future. The influence of dark matter will persist, silently shaping the galaxy's evolution even as visible structures change dramatically. Spiral arms may dissolve and reform, stars may migrate into new regions, and satellite galaxies may be assimilated into the halo, but the invisible mass distribution will continue to provide the gravitational glue that preserves coherence in the system. In this sense, dark matter ensures continuity amid transformation, a stabilizing force that allows the Milky Way to survive dramatic events such as mergers and internal instabilities without disintegrating. Emotionally, contemplating the Milky Way's future evokes both awe and humility. Awe at the immense timescales and energies involved, from the graceful drift of stars to the cataclysmic collision with Andromeda. Humility in recognizing that humanity's existence is but a fleeting moment, a transient observer within a galaxy that has existed for over 13 billion years and will continue evolving for billions more. The future of the Milky Way is both magnificent and indifferent, a reminder of the vast, ongoing processes that shape the cosmos beyond the scope of human experience. From a narrative perspective, the future of the Milky Way provides a sense of closure and anticipation, tying together the past and present while projecting the galaxy's story forward. It underscores the themes of continuity, transformation, and interconnectedness, showing how every star, gas cloud, and cluster is part of a larger cosmic narrative. The spiral arms, bulge, halo, and core are all components in an ongoing drama, shaped by gravity, dark matter, and cosmic time, each contributing to a future that is both predictable in its broad strokes and unpredictable in its details. Ultimately, the Milky Way's future is a testament to the grandeur and dynamism of the universe. It will continue to evolve, collide, and transform, producing new stars, altering structures, and engaging in cosmic interactions that extend far beyond our solar system. It is a story of creation and destruction, order and chaos, continuity and change, unfolding on a timescale that humbles human perspective. By understanding this future, we gain not only insight into the galaxy's destiny but also a deeper appreciation for the fleeting, precious moment we occupy within its vast, ever-changing expanse. The Milky Way is not merely a backdrop to our existence. It is a living, evolving entity, and its future is a narrative as awe-inspiring, intricate, and immense as the universe itself. The Milky Way does not exist in isolation. It is part of a vast cosmic community known as the Local Group, a collection of more than 50 galaxies bound together by gravity and engaged in a slow, intricate dance that has been unfolding for billions of years. This neighborhood includes not only the massive Andromeda Galaxy and the Triangulum Galaxy but also a host of smaller dwarf galaxies, globular clusters, and satellite systems. From the perspective of the Milky Way, these companions are both distant and influential, their gravitational pull shaping stellar orbits, perturbing the galactic halo, and occasionally delivering bursts of gas and stars that feed star formation. Understanding the Milky Way's place within the Local Group is essential for grasping the broader context of galactic evolution, revealing that our galaxy's story is entwined with the fates of its neighbors. The Milky Way and Andromeda are the dominant members of the Local Group, each containing hundreds of billions of stars and extensive dark matter halos. Though separated by millions of light-years, their mutual gravitational attraction is inevitable, drawing them toward a future collision billions of years from now. This interaction is part of a larger pattern of motion within the Local Group, where smaller galaxies orbit, interact, and are sometimes absorbed by their massive companions. Streams of stars from disrupted dwarfs crisscross the halo of the Milky Way, providing visible evidence of past mergers and a record of the ongoing dynamism within the group. These processes illustrate that galaxies are not static, solitary entities but participants in a network of relationships, constantly shaped by proximity, gravity, and cosmic time. Smaller satellite galaxies, such as the Large and Small Magellanic Clouds, play a particularly active role in the Milky Way's evolution. As they orbit our galaxy, their gravitational influence induces waves in the spiral arms, perturbs the motion of stars in the outer disk, and can even trigger star formation by compressing interstellar gas. These dwarf galaxies are gradually being assimilated, stripped of stars and gas that join the Milky Way's halo and disk, a process that has been occurring repeatedly over cosmic time. Observing these interactions allows astronomers to reconstruct the Milky Way's accretion history, providing insight into how galaxies grow by consuming smaller companions, a process fundamental to understanding the hierarchical nature of cosmic structure. The Local Group itself is embedded within an even larger structure, the Virgo supercluster, a filamentary arrangement of galaxies stretching across tens of millions of light-years. The Milky Way, Andromeda, and Triangulum are but local nodes in this vast web, connected through gravity and dark matter, moving along filaments shaped by the distribution of mass in the universe. The motions of galaxies within this supercluster influence the timing and dynamics of future collisions, the inflow of gas, and the evolution of stellar populations over billions of years. From this perspective, the Milky Way is simultaneously a galaxy, a cluster member, and a participant in a supercluster scale system, highlighting the layered, hierarchical nature of cosmic structure. Interactions within the Local Group are not always gentle. Gravitational encounters can distort galactic disks, induce tidal tails, and create streams of stars stripped from their original hosts. These features are subtle records of past interactions, allowing astronomers to trace the galaxy's history with remarkable precision. The Milky Way's halo in particular bears the imprint of these mergers, filled with ancient stars and globular clusters that originated in other galaxies. Even in its relatively quiet disk, the cumulative effects of these interactions can shift stellar orbits, alter the structure of spiral arms, and influence star formation rates. The galaxy is thus not merely an isolated spiral but a dynamic participant in a crowded cosmic neighborhood, constantly responding to external forces while shaping its internal evolution. Emotionally, the Local Group evokes a sense of connectivity, scale, and cosmic choreography. Connectivity in the recognition that no galaxy exists in true isolation. Every system interacts gravitationally with its neighbors, exchanging matter, energy, and momentum. Scale in the awareness that even the Milky Way, vast as it is just one of dozens of galaxies in a relatively small region of space, each with its own history, structure, and destiny. Cosmic choreography in the realization that these interactions, collisions, and mergers are slow, deliberate, and predictable over billions of years, yet produce outcomes both intricate and astonishingly complex. Understanding the Local Group provides perspective on the Milky Way's place in the universe, emphasizing both its individuality and its interconnectedness. From a scientific standpoint, studying the Local Group allows astronomers to test models of galaxy formation, dark matter distribution, and cosmic evolution. By observing the motions of satellite galaxies, the structure of tidal streams, and the dynamics of mergers, researchers gain insight into the processes that govern all galaxies. The local group becomes a laboratory for understanding hierarchical growth, the role of dark matter, and the interplay between gravity and cosmic time. In this sense, the Milky Way's future, history, and present state cannot be fully understood without considering its place within this local cosmic community. Ultimately, the Milky Way's membership in the local group underscores the interconnectedness of the cosmos. It is not a solitary island drifting through empty space but part of a gravitationally bound network of galaxies, each influencing and being influenced by the others. From distant dwarf galaxies to the massive Andromeda, from tidal streams to dark matter halos, the Milky Way participates in a slow, elegant dance that has persisted for billions of years and will continue for billions more. This context reveals that the galaxy's evolution, structure, and destiny are not only determined internally but are deeply entwined with its cosmic neighborhood, highlighting the intricate web of forces, time, and matter that shapes the universe on every scale. Humanity occupies a tiny, fragile corner of the Milky Way, drifting quietly in the Orion Arm, far from the galaxy's turbulent core and the sparse halo. Our solar system formed from the remnants of ancient stars, enriched with heavy elements necessary for life, and Earth emerged as a rare oasis where life could flourish. Compared to the galaxy's 13-billion-year history, human existence is an imperceptible blink, yet it allows us to observe, study, and understand the Milky Way's vast structure, from spiral arms to the dense core, the halo, and the invisible dark matter holding it all together. This perspective evokes both awe and humility. Awe at the galaxy's immense scale and beauty, and humility in recognizing our small, fleeting place within it. Our position is fortunate, relatively safe and stable, allowing life to develop and giving us the opportunity to explore the cosmos. Though we are tiny in comparison, humanity is part of the galaxy's ongoing story, a conscious observer capable of reflecting on its history, present dynamics, and future evolution. In understanding our place, we connect intimately with the Milky Way, bridging the scales of cosmic time and space, and embracing both the fragility and wonder of life in a universe defined by immense forces, immense distances, and continuous motion.